All right, the last talk of this session will be by Christian Mayens on catalytic decoupling. It's a different title in the thing here. Catalytic decoupling, oh, I see. It's two talks that have been joined together into one. So joined with deconstruction and conditional erasure of correlation.
Thank you. Yeah, thanks for the introduction, and I want to thank the organizers for giving me the opportunity to give this talk. Yeah, as mentioned, this is a merge talk of these two papers, which is joint work with quite some people: Mario Berta, Fred Dupuy, Renato Renner, Matthias Christandl, Fernando Brandao, and Mark Wilde. Yeah, it kind of makes a lot of sense that these have been merged to me, because they are just two generalizations of the same concept. So what I'm going to do now is first introduce that concept and then continue to present the two generalizations. And that concept is decoupling, or a very closely related concept is erasure of correlations, and these I want to present now first or explain in an introduction, so we can go on to generalize them. So, what is decoupling? The decoupling technique basically boils down to the idea to destroy correlations between two quantum systems by only acting on one of them with a local noisy quantum channel. And this has been a very useful proof tool in many areas of quantum information theory and beyond, like, for example, quantum Shannon theory, thermodynamics, solid state physics, and also black hole radiation, although I don't understand that very much, but I've been told so, at least. So if we look at the details, it's maybe very instructive to explain the exact protocol in this pictorial way. So we start out with the bipartite quantum system that has two parts, A and E. And this bipartite quantum system is in some mixed state, rho AE. Now, we subdivide the system A into two parts, A1 and A2. We apply a unitary to the A system here, and then we take the partial trace over A2. This is basically the noisy part of the map. And then if we did everything right, then the remaining system A1 is in a product state with system E. Now, of course, the question the information theorist asks now is how big do we have to choose this A2 system that we are getting rid of to achieve this task, to render the system product afterwards? Because just as a sanity check, there exists some size of A2 that achieves this, because if we choose A2 to be all of A, then it's trivially achieved for any unitary. As it turns out, the relevant quantity here is the quantum mutual information, at least in the so-called asymptotic or IID setting. So that is the setting where the quantum state we are looking at is a tensor power, is just many independent copies of another quantum state sigma. So then the optimal size of this system A2 that we got rid of is equal to the quantum mutual information in first order in N. And this was essentially first observed by Horodetzky, Oppenheim, and Winter in their work on state merging. They had it in a slightly different form, but essentially it's equivalent. So this gives us an operational interpretation of the quantum mutual information, and this is very nice because although the quantum mutual information is easily generalized by just generalizing the classical formula, it's not clear a priori whether the interpretation generalizes as well. So slightly before that work on state merging, there was a work by Groisman, Popescu, and Winter where they introduced a task that's called erasure of correlations. And that is very similar to decoupling, except that they didn't apply it to anything, any other tasks, but they considered the erasure of correlations the task itself. So let's look at this in detail. It's basically almost the same as before. We start with the bipartite quantum system here that has parts A and E. But this time, we, instead of a partial trace as a noisy map, we apply a so-called random unitary channel, which consists of choosing a set of 2 to the k unitaries, and then basically flipping k coins, and so randomly choosing one of the 2 to the k unitaries. And then we hope that afterwards the system ends up in a product state. Of course, the question again is how big do we have to choose k here to achieve this task? And it turns out the answer is almost the same. In the asymptotic setting, we need a number, basically an amount of noise in this process that is again equal to the quantum mutual information. And yeah, this is of course an operational interpretation of it, and this should not be considered very surprising in the sense that decoupling and erasure of correlations are really actually more or less 2 sides of the same coin. So if we have a protocol for decoupling, then we get one for erasure of correlations, and the other direction becomes true under a slight generalization of the task that we will see later. So this was the introduction to decoupling and erasure of correlations, and now I want to continue by generalizing these paradigms in 2 ways. So first I want to present a one-shot generalization of this, which we call catalytic decoupling, and here this quantum mutual information, this familiar quantity, is replaced by a one-shot version of it, which is called the max mutual information. And then I will continue in the second part to generalize decoupling to the setting with quantum side information. And here, perhaps not very surprisingly, the quantum conditional mutual information plays the role of the relevant information theoretic quantity. Okay, let's start with catalytic decoupling. So to motivate our work on catalytic decoupling, let me present some previous work. So this is actually this is a one-shot decoupling theorem by Dupuy, Berta, Wohlschläger, and Renner. So it reads like this: if we have a bipartite quantum state, then we want to decouple A from E, and we choose some decomposition of A into 2 parts, A1 and A2. Then if we choose A2 large enough, according to this lower bound that I will explain in a second, then there exists a unitary such that if we apply the unitary and take subsequently the partial trace over A2, then the system ends up in an approximate product state. However, notice that this doesn't only simply achieve that the system is in a product state, but what is more, the decoupled part of the system, this A1 here, is in a maximally mixed state. And this is also reflected by the fact that we get, as a cost function here, as this minimal size of A2, we get a difference of smooth Rényi entropies. And basically the unconditional versions of these Rayleigh entropies are defined in this little graphic here. So this is the spectrum of some quantum state rho. The min entropy is the negative of the logarithm of the maximum eigenvalue, where the max entropy is the logarithm of the size of the support of the spectrum. And these epsilon, this little epsilon, this shows that this is a smooth version, a so-called smooth version of the Rayleigh entropy, which means that the quantities are optimized over an epsilon ball around the state rho. So in particular, because of the definition of these quantities, this difference here can be very large, even in cases where the two systems should actually be considered decoupled. And that is if we have a product state already between A and E, but maybe the system A is in a state that's very far from a mixed state, from a maximally mixed state. In comparison, if we take the situation for the IID situation again, then this lower bound here, as I said, will just be in terms of the quantum mutual information. And this has all the properties that we want. It becomes 0 for product states, and also it can be shown that this is optimal. Okay, so there has been some previous work overcoming the problem that I described in the last few slides, and that is in the specific application of one-shot quantum state merging. I have not explained what this is, this one-shot quantum state merging, but let me anyway present or like mention these results to basically be able to refer to them later. Oh, sorry. So Berta, Christandl, and Renner, they showed that one-shot quantum state merging is actually possible with a quantum communication cost that is proportional to this max mutual information, which will play the important role in the characterization of catalytic decoupling. And they use the standard decoupling theorem that I have presented to you in the last few slides, but on top of that they need a concept called embezzling states, which was introduced by Van Dam and Hayden. And then there was some more recent work improving over this bound in the lower order term here by Anshu, Devabatini, and Jain. Actually, their work is on state redistribution, an even more complicated task, but it also has this corollary about one-shot state merging, and it uses a completely different technique that's called a convex split lemma. So these were basically like tailored fixes to the problem that I presented in the application in these quantum Shannon theoretic applications. And now what we were able to do is somehow distill these fixes into and unify them into a generalized decoupling paradigm that works in the one-shot setting. This is what we call catalytic decoupling, and it generalizes decoupling in two ways. On the one hand, we drop this condition that the decoupled system should be in a maximally mixed state. And on the other hand, we also allow that before the decoupling procedure is started, a mixed ancilla state is appended. So to show this in this pictorial way, as I have presented the previous concepts, we start with this bipartite quantum system again with the systems A and E. But this time, we append some product system, A prime, in some fixed state. And now we continue in the same way as in regular decoupling. We divide this joint system, A prime, into two bars, A1 and A2. We apply unitary, and we take the partial trace over A2. And we hope that afterwards the system is in a product state. And note here that it's very important that we focus on the size of this system A2 that we trace out, because if we would focus on the size of the system that is decoupled here, that we could make arbitrarily large, but by just appending a large ancilla. But we focus on this the system, the size of the system that we take the trace over, and that is basically corresponds to the amount of noise we have to inject, and there we have we expect to get a lower bound for that. Yeah, the question is, of course, how big do we have to choose A2 in this generalized case? This should be smaller than in the case of regular decoupling, because we have relaxed the conditions. We have given us more opportunities to what kind of operations to apply by appending this ancilla, and we have dropped this condition of randomization. So this new paradigm can be completely characterized now, and that's what we've done. If we again start with the bipartite quantum state rho AE, then we pick some accuracy for the decoupling. Then catalytic decoupling with this accuracy epsilon can be achieved with the remainder system size log A2 that's approximately equal to 1/2 times the smooth max mutual information. And this max mutual information, now it's maybe time to give a definition. This is defined in terms of this max divergence or max relative entropy, and it involves this minimization here, and the max relative entropy is just defined in terms of this minimization of the simple operator inequality. And this little epsilon here, this signifies that this is a smooth version again, which means that this quantity here is minimized over an epsilon ball around the state rho. I said log A2 is approximately equal to this quantity, but yeah, to be more precise, this means up to terms that are much slower if the dimensions go up. We also can provide a converse statement, which means that catalytic decoupling is impossible whenever we try to do it with a smaller system, A2, than 1/2 times the max mutual information. So I mentioned that this is unifying these two previously existing techniques, and this is reflected in the fact that we have two proofs of this theorem, where one using with using the techniques from these two works respectively. Okay, so maybe I should go quickly through this slide to get to the second part. We can show an asymptotic equipartition property, that is, we recover the statement about regular decoupling in the asymptotic setting, and this shows that in this case the ancilla becomes unnecessary, and the randomization condition is redundant, which is also to be expected because all marginals in the asymptotic setting are anyway have a flat spectrum. And because we get a quite tight characterization of this task, we can also give a second order term in the asymptotic expansion in terms of this mutual information variance and the usual inverse cumulative normal distribution. And as promised in this case with ancilla, this random unitary channel model and the partial trace model are completely equivalent. Okay, this was the first part of the talk, so let's move on to the second part, which we call conditional erasure of correlations. And this is now a completely different setting. Here we stay in the asymptotic setting of many independent identically distributed copies of some state, but we add quantum site information. So this means we are talking about tripartite quantum states, rho A ER. And there we have the so-called quantum conditional mutual information, which is given by this formula. And it has the property that it measures conditional correlations between A and E conditioned on R in the following very precise sense that was basically discovered by Fauci and Renner. And that is that if we just look at a tripartite quantum state here, rho AER, and now maybe we lose the system A, so we only have rho ER left. Now we try the following. We just try to recover A, the system that we lost, by only applying a quantum channel to R. This quantum channel we also call R usually, because it's a recovery channel. And then in the case where this quantum mutual information here is small, the quantum conditional mutual information, then we can achieve that this recovered state is approximately equal to the original state. And in this pictorial, in this picture, these lines, they are supposed to be correlations. And you can see, because we were able to reproduce the state by just operating on R, this line here somehow vanished and we couldn't recover it. So it seems like, or that's the case, it hasn't even been there in the beginning. So there's no direct correlations between A and E. In other words, all correlations between A and E are somehow mediated through R. And in this case where this recovery is possible, we say that E to R to A is an approximate quantum Markov chain. Yeah, as I said, this is just to conclude that this quantum conditional mutual information here measures conditional correlations in this very precise sense. So recall that this erasure of correlations that I presented in the introduction, this task needs an amount of noise that's equal to the quantum mutual information. So a natural question is, of course, can we erase conditional correlations as measured by the quantum conditional mutual information by injecting an amount of noise into the A marginal that is proportional to this quantum conditional mutual information. Unfortunately, this is not the case. There's even a classical counterexample to this idea, which is kind of quite simple, but unfortunately it takes a bit too long to explain for this short talk. What is more, there's some previous work by Wakakua et al. Which characterizes this task, this task of erasing the conditional correlations by locally acting on this A system here. But they were able to characterize it in terms of some function that's discontinuous in terms of the quantum state, and in general much larger than the quantum conditional mutual information. However, if you think of the classical case, there's one situation which is, or one modification of the task where it's obvious that we can somehow salvage our idea of finding an operational interpretation of the quantum conditional mutual information, and that is by basically, instead of applying just a local operation on A, we apply an operation on A conditioned on R. Because if we condition on R, then we are back in the classical case, and then we are back in the bipartite setting. Okay, so let me quickly introduce the task of quantum state redistribution, because that's what we will need for characterizing conditional erasure of correlations. So this is a task where we have two players, Alice and Bob, and a referee R. And Alice has two quantum systems, C and A. Bob has a quantum system B, and the referee has his quantum system R. And the global state is pure. So their task is that Alice wants to send her system A to Bob. while she can operate it on A and C. But the task is to keep, for Alice, is to keep C and send A to B. To achieve this task, they can also use some entangled resource here. And what is nice about this task, which one could also call quantum source coding with side information at both the encoder and the decoder, is that the optimal communication rate that is necessary for Alice to send this system is given by the conditional quantum mutual information. This was shown by Devetak and Yard. So after this little intermezzo, let's come back to our task of conditional erasure. And there we have this tripartite quantum state. And now we just introduce the concept of a quantum conditional operation on A conditioned on R. And for this, we slightly relax the classical idea by saying that we operate on AR, but we want to leave the RE marginal approximately unchanged. On top of this, as in catalytic decoupling, we allow appending an ancilla. So in this, explained in these pictures again, we have the tripartite quantum system with systems A, E, and R. Now we append an ancilla. We apply unitary to these three systems, R, A, and A prime, but under the condition that these E and R, the joint ER system here is approximately unchanged. After that, we continue like before. We subdivide the A systems into two parts, A1 and A2, take the partial trace over A2, and then hopefully we have achieved our task of conditional erasure of correlations. But actually, there are kind of two different tasks. There's two different results one could ask for. One of them is to render, as described on a few slides ago, to render E to R to A1 an approximate quantum Markov chain. That is, to make this A1 system here recoverable from R. But we could also ask something stronger, where we ask A1 to be completely in a product state with this ER system. And the first task we call deconstruction of correlations, and the second task we call conditional erasure of correlations. And of course, the second one implies the first one because a product state is for sure recoverable. And now we were able to characterize this in an asymptotic setting where we show that conditional erasure, the stronger task here, is equivalent to quantum state redistribution, where basically communication rate in the quantum state redistribution case it translates into noise rate in the conditional erasure case. Also, we have a converse statement for the weaker task, which matches the direct statement for the stronger task. So that means that these two tasks here have both the same optimal noise rate asymptotically. And we ended up with a new operational interpretation of the quantum conditional mutual information. Okay, so we're at the last slide. What did we do today? We generalized the decoupling paradigm or erasure of correlations to two new settings, which is two different settings. One is the one-shot setting here, where the max mutual information replaced the mutual information, and then also to the setting with side information, where the quantum conditional mutual information was the relevant quantity. And these two generalizations have some applications. So catalytic decoupling can be used to give a simple proof for the achievability of one-shot state merging. And the conditional erasure of correlations paradigm can be used to give operational interpretations of the quantum discord and squashed entanglement. Okay, this is it. Thanks for your attention, and I'm open to your questions.
Okay, questions?
So in catalytic catalytic decoupling? Do you require that the ancilla is returned in the same state, or what is catalytic about it?
So somehow there's two ways. First, we can actually hand back the ancilla in approximately the same state with the same approximate quality as the whole decoupling procedure. With the same error as the decoupling works. This is, of course, not catalyticity in the thermodynamic sense, because this way, like this, the distance notion we use is the trace distance, and then you basically, for large systems, you can do a lot of things in thermodynamics if you allow small trace distance error.
Other questions?
Do you have any control?
The mic is right on its way.
I was just wondering how large these catalysts need to be in order for the theorems to work.
That is a very good question, we have basically, I have to say, we have no idea how large they have to be. So our achievability results use huge catalysts. However, we don't even have a proof that it is necessary, the catalyst. Yeah.
More questions?
Also, maybe I can say one more sentence about this. One interesting question is, let's assume the catalyst is necessary in the single shot setting. Then, of course, you get the finite block length question, where basically you're in an intermediate regime where your one-shot protocol requires huge amount of ancilla, but you should be approaching the asymptotic setting where the ancilla definitely becomes unnecessary. So, yeah, this is also something that's maybe interesting to look at.
Questions? Just ask a very naive question. You mentioned that the decoupling techniques were used as proof techniques in quantum Shannon theory and other areas. So with these new results, what further applications, what new kinds of things would these let you prove?
So somehow, as I said, catalytic decoupling can be used for this single-shot quantum state merging, but this result is not new. It has been proven before. Just now, we can prove it in the same way as in the asymptotic setting, because we have this catalytic decoupling that we can apply black box. Beyond that, I mean, conditional erasure it's equivalent to quantum state merging, to quantum state redistribution. So actually, it can be used to prove achievability of quantum state redistribution. But beyond that, we didn't find for now any further information theoretic applications.
For now. Other questions? People are looking hungry, I guess. So
we shouldn't keep people from
I just observed, it just occurred to me that the speakers at this conference are the red shirts, but I'm sure there's nothing to worry about. So thank you very much. Let's thank Christian again and all of the speakers.